We have learned that a function is a relation in which every x value has exactly one y value. We have also learned that there's different ways to present that function. We can do so as a list of ordered pairs, or we can write them as a mapping. The first set is called the domain, the second set is called the range. Now, if I take all the values of the domain and I order them on a horizontal axis called the x-axis, and I take all the values of the range and order them on a vertical axis called the y-axis, and I plot the ordered pairs in the plane, then another way of representing a function is as a graph. If I have a graph, it is very easy to determine if we are dealing with a general relation or a more specific function, easier than applying the definition. In 3.1.3, we learn about the vertical line test. To use the vertical line test, we must have the graph of the function. So, number 1, graph the function. And here's the test. Number 2. If a vertical line, vertical means up and down, if a vertical line can be constructed that intersects the graph in more than one point, the graph is not a function. If a vertical line can be constructed that intersects the graph in more than one point, then the graph is not a function. This is actually testing the definition that every x value can only have one unique y value in a visual or geometrical way. Example 2, determine if the following are functions. Then give the domain and the range in interval notation. Now remember, when we studied linear inequalities in section 1.2, we learned interval notation. That's going to come in really handy here as we apply that to both the horizontal x-axis and the vertical y-axis in describing the domain and range of a function. Let's answer the easy question first. The easy question is, determine if the following are functions. So looking at this first graph, I want to construct several vertical lines and see if I can intersect in more than one point. Now, if I construct a vertical line in multiple locations on this graph, I am never going to be able to intersect that graph in more than one point. Therefore, this is the graph of a function. Let's consider example C. If I construct a vertical line here, notice I'm intersecting the graph in more than one point, and I can do this in several locations. Since I can intersect the graph in more than one point with a vertical line, then this is not a function. Now, notice how this vertical line test works. If I observe the ordered pairs that this second vertical line intersects, this is the ordered pair -1, 2, and this is the ordered pair -1, -2. Notice what the vertical line has identified. I've got one x value with two different y values. Remember, we said an x value cannot repeat. Every x has to have a unique y. Here we have one x value, that is -1, with two different y values. Therefore, it is not a function. So the vertical line test is, again, a visual way of testing the definition of a function. And in my opinion, it's much easier than looking at a list of ordered pairs. What about example B? Do you think example B is a function? The answer is no. This is not a function because I have found a vertical line that intersects in more than one point. How about example D? Is this a function? Absolutely. We can construct several vertical lines. It is not possible to intersect twice. So this is a function. We will spend a lot of our time in college algebra studying functions. At this point, we can identify a function. Now, let's talk about domain and range, identifying the domain and range of a function from a graph. Now, the domain, remember, is the set of all x values used on the graph. When I describe the domain in interval notation, I am describing x values, and I'm going to describe them from left to right. So the leftmost x value to the rightmost x value. When we identify the range of a function, we're thinking in a different dimension. We're thinking about the y values. And we quote this from lowest to highest. So let's see if we can determine the domain of our first example. So what I want to do is identify the leftmost point on this graph. So if I follow this parabola to the left, notice there's an arrow on the end. What that means is it is going to continue opening wider and wider and wider to the left. There is no leftmost point. So in this case, we say the leftmost value of our domain is negative infinity. And remember, with interval notation, we always use parentheses with infinity. Now, let's see if we can find the rightmost x value. If I trace this parabola to the right, again, I encounter that arrow on the end. That means this parabola is continuing to get wider and wider and wider, even beyond the grid that I can see. Therefore, there is no rightmost value, and we would say the domain then is negative infinity to infinity. If I imagine holding a light above this parabola, that U shape is called a parabola, and I think what sort of shadow would be projected onto the x-axis? Well, the entire x-axis would be shadowed by that parabola. That means I've used every possible x value from negative infinity to infinity. Okay, now let's change dimensions. We're going to do the same thing, but we're going to be looking at the parabola from lowest to highest, and this time I'm going to be thinking about y values. So I want to start by finding the lowest point on the graph. I have found the lowest point on the graph at that vertex. Notice the y value here is -1. So the lowest y value, or the lowest elevation on this parabola, is 1. I'm going to use a bracket because it is included on the graph. Next, I want to find the highest point on the graph. Well, the arrows on the end indicate that it's continuing to get taller and taller and taller. So I will use every possible y value on up to infinity. So there is no highest y value, no highest point. It just keeps getting higher and higher. So then the range would be from 1 to infinity. So let's practice that again. Looking at example C, we want to identify the domain. The domain is the set of all x values used on the graph, and we read this from left to right. So we want to find our leftmost point on the graph. Well, notice that this parabola continues moving to the left indefinitely. So the leftmost x value is negative infinity. The rightmost x value, I can find a rightmost point. The corresponding value here is x equals 3. This is ordered pair 3, 0. The x value that's used there is 3. So the domain is negative infinity to 3. Let's figure out the range. The range is the lowest y value to the highest y value. Well, because this parabola continues getting lower and lower and lower, there is no lowest point, and this part keeps getting higher and higher and higher, there is no highest point. Our range is negative infinity to infinity. Now, observe that these domains and ranges are different from what we did in the last section. On example 1a and 1b, when we listed the domain and range, we had just a list of points, because in those functions, we had specific ordered pairs. It wasn't a continuous graph. Because in these examples, we have a continuous graph, our domain and ranges are in interval notation. They're describing everything between and including the values used in the interval notation. So don't be tempted to list ordered pairs for the domain and range of a function. Let's try example B. The domain, again, is the set of all x values. Remember, the horizontal axis is my x-axis. X values from left to right. So I'm going to find the leftmost point on the graph, and I'm going to observe its x value. its x value is -4, and it is included as a point on the graph, so we will use a set of brackets. Now, let's find the rightmost point. Here's the rightmost point. I want to read its x value. It looks like its x value is 2. So the domain is all the x values between and including -4 to 2. So it's like we're sweeping the graph from left to right. Now, when we go to the range, we're going to sweep the graph from lowest to highest. So really, you're just reading the 2 dimensions of this graph. Let's find our lowest point. Here's our lowest point. Now be careful here. I want to pick up the y value. The y value here is 0. The ordered pair of this point is -1, 0. My lowest y value is 0. Let's find the highest point. This is the highest point. Let's observe that the ordered pair there is 6. I'm looking for the highest y value, and so I would choose the y value 6 there. So again, domain is x values left to right. So we're sort of sweeping it in this dimension. And the range is going to be my y values lowest to highest, so we're reading it in this direction. So again, we're sweeping 2 dimensions of the graph. Let's do example D, finding domain and range. Okay, let me just give you a pop quiz. What is the leftmost x value used on this graph? I hope that you recognize that there is no leftmost x value. It is in continual motion to the left, so we'll set the left part of the domain to -infinity. What's the rightmost x value used on this graph? Well, because it's continually in motion to the right, even beyond the grid that we can see, there is no rightmost x value, so our domain is -infinity to infinity. Now, let's apply that same interval notation, but in the vertical direction, and we're going to change our minds. We're not thinking about x anymore. We are thinking about y. What is the lowest point on this graph? Is there a lowest point? I hope you said no, there's not a lowest point. It keeps going down forever. Therefore, the bottom part of our range is -infinity. Okay? What's the highest point on this graph? Well, all of these points sort of tie for the highest point. What's our highest elevation? The highest elevation goes all the way up to 3. So the range is from -infinity to 3. So again, for the domain, we are sweeping the graph from left to right, thinking about what sort of x values are being used. For the range, we're sweeping the function from lowest to highest, thinking about what sort of y values are used. And we are using the correct notation that we learned with interval notation in section 1.2. Let's consider one more perspective of how functions can be presented. Remember, we looked at them as a list of ordered pairs, as a mapping, now as a graph. The most efficient way to express a function or a relation between 2 sets is in equation form. So we want to be able to look at an equation and determine if it is a function. A function will be able to be written in such a way that y is isolated and it's equal to a single expression involving x. Now, if we have a y squared or a y to the 4th or some sort of even power, then we will not be dealing with a function. Okay, so I'm going to give you lots of notes on this page. Note, if an equation contains an even power of y, it is not a function. Okay, let me give you a quick example. I'm going to draw your attention here to example C. If I were to solve for y, I would take the square root of both sides, and that would give me 1 positive and 1 negative root of x plus 2. So I could plug in one x value and evaluate. I would end up with 2 different y values. So that's going to happen anytime you have an even exponent on y. If you have an odd exponent and you can isolate y, then you're dealing with the function. So look at example A. Y is isolated. It's equal to x squared. So whatever number I plug in for x, I'm going to get out a unique value for y. Y is isolated. It's equal to a single expression. So this one is a function. Example B, if we were to do the algebra and solve for y, for example, we would subtract 5x from both sides and we would divide by 4. We would have y isolated. This one is a function. Okay, you do not have to solve for y to understand that. Remember, if you have an even power of y in the equation, it is not a function. Otherwise, it is a function. So what about example D? Is that a function or not a function? That one is a function. Notice y is isolated. It's equal to a single expression involving x. There's no even powers of y, so it is a function. Let's come back to example C. This was our example of something that is not a function. Example E, you may not like that, but it is a function because y is isolated and it is equal to a single expression involving x, and there's no even powers of y. It's a complicated function, but it's a function nonetheless. How about example F? Is that a function? Yes, this one is a function. There's a lot of different types of functions that we will eventually classify, and here our goal is just to get used to what a function looks like. Example G, y is not isolated, but I could isolate it by dividing both sides by x, and I could see I'm dealing with an odd power of y, so this is a function. And the last one, what do you think? Is that a function? Yes, y is isolated. It's equal to a single expression involving x. There's no y squared, no plus or minus there. So that one is a function. So almost every equation on this page is a function. These are the types of structures that we will be examining. Next, we want to state the domain in interval notation. Couple of notes I want to give you for the domain. First, we're going to assume that the domain is negative infinity to infinity unless we run into two problems, okay? Two things you want to watch out for where you have to make a restriction on the domain is a radical or a rational function, okay? So let me add a couple of notes. I need some space here. Number one, to find the domain of a radical function, that's one that contains a square root or a cube root or maybe a 1/2 power or a fraction power. To find the domain of a radical function, set the radicand greater than or equal to 0 and solve for x. The result will give our domain as an inequality, and we can convert that to interval notation, okay? So for a radical function, I have to make a restriction, and we'll do an example. The second thing you want to watch out for is a rational function, or a function that has a fraction. To find the domain of a rational or fraction function, exclude values which create a 0 in the denominator. Okay, and we'll do examples of that. So the two special types of functions that you want to watch out for are radical and rational. That is, those that have a square root or a cube root or something like that, or a rational function, a function that contains a fraction. So on example A, y equals x squared. It is neither radical nor rational, so the domain is negative infinity to infinity. Okay, and in fact, the graph, if you graph that on your calculator, you'd see a parabola. It will be very similar to the shape of example A. The domain would be negative infinity to infinity. Example B, notice this is a linear equation in two variables. If we were to graph it, it would be a straight line. And the domain of a line is always negative infinity to infinity, as long as it's not vertical or horizontal. So if I'm dealing with either a parabola or a line, the domain is negative infinity to infinity. The next example is not a function. It is merely a relation, but when we solved for y, we obtained a radical function. So to find the domain of this radical relation, I'm going to take the radicand out and set it greater than or equal to 0. What I'm doing there is saying that this number better be positive, because if it's negative, we're going to get an imaginary number, right? And I can't plot an imaginary number in the real plane. So if I solve this very simple linear inequality, looks just like the inequalities we saw in section 1.2, the solution I obtain is x greater than or equal to -2. If I rewrite that in interval notation, it would be from -2 to infinity. So the graph is going to have x values from -2 to infinity. Another radical function is in example D. We want to find the domain of that radical function. So I'm going to take the radicand out and set it greater than or equal to 0 to say that radicand needs to be positive or 0. Otherwise, if it's negative and I take the square root of it, I'm going to get an imaginary number. Then we have problems plotting that in the real plane. Let's solve this linear inequality in one variable for x. Notice on the next step here, to solve for x, I have to divide both sides by -2. What did we learn about inequalities when you divide by a negative? Remember, we got to reverse the direction of that sign. So our domain is x less than or equal to 7/2. So in interval notation, this is from negative infinity to 7/2 with a bracket. Now, you can verify this with your calculator. To graph a function on your calculator, you press the y equals button. Okay, and if there's anything there, you can clear it out. And we're going to enter our function. It is the square root, so second square root, let me switch over here, of 7 minus 2, and then my variable key is the key next to that green alpha button. Okay, and then I'm going to type my graph button in the top right, and I'll be able to see the graph of this function. Now, if your graph doesn't look like my graph, one thing you might need to do is adjust your viewing window. So if you'll type zoom number 6, zoom standard, then that sets your viewing window from -10 to 10 on the x-axis and -10 to 10 on the y-axis. Now, we predicted from our analysis that the domain is negative infinity to 7/2. 7/2 is about 3.5. Notice on our graph, the leftmost x value is negative infinity, and the rightmost x value is right there at 3.5. So I can even see the domain by looking at the graph. I can verify the work that I've done by hand. So that deals with square root functions. Example E is an example of a rational function. When we find the domain of a rational function, the one worry we have is we got to make sure that denominator is not equal to 0. If the denominator has a value of 0, then we would be attempting an illegal operation, that is to divide by 0. Even the calculator knows that I cannot divide by 0. For example, if I try to enter 10 divided by 0, the calculator tells me I have made an error. That is not a valid calculation. So we're going to make sure that we do not divide by 0 by saying, okay, that means x cannot be equal to 5. So the domain in English as a description would be all real numbers except 5. Now, how do I get that in interval notation? Well, I want to think about every number on the number line except for 5. I'm going to come and pluck this one number off of that number line, and then I'm going to use interval notation to describe everything that's left. The leftmost value here is negative infinity, and then I can't use 5, so I'm going to come just right up to the left of 5, but I'm going to use my parenthesis to indicate that I'm not including 5. Then I'm going to jump over 5 and describe the values on the right side. That's going to look like 5 to infinity. In the middle, we use this symbol U. That represents union. So the domain is all real numbers except 5, which in interval notation means everything to the left of 5 and everything to the right of 5. So we get 2 pieces for our domain there. We will spend time studying rational functions extensively, and we're going to do this. We're going to have a lot more practice on this. So don't be overwhelmed at this point. We will get more practice in the future. Example F, notice we have x plus 1 to the 1/3. If I rewrite that in radical form, this is the cube root of x plus 1. Now, it is possible to take the cube root of a negative number and get a real number, but it is not possible to take the square root of a negative number and get a real number. So if you have an odd index on your radical, no worries. The domain is negative infinity to infinity. Okay, we're looking at a lot of different functions at once on one page. We will take the time to classify these individually one by one and understand these functions in more detail. For now, if I wanted to graph this on my calculator, I could look at it and make sure, that I have correctly identified the domain. So I'm going to type it in, x plus 1 to the 1/3. I'm going to graph it, and I'm going to observe the leftmost x value is negative infinity and the rightmost x value is negative infinity. Okay, so it helps to look at these with your calculator. Example G, we have a rational function or a variable in the denominator. So for the domain, we want to make sure that denominator is not 0, right? We're going to set it not equal to 0. Now, in words, the domain is all real numbers except 0. So if I think about the number line here, I'm going to pluck out that one value, and that divides my interval into 2 pieces. So our domain is negative infinity to 0. Use parentheses here to skip over 0, and 0 to infinity. So there's the left of 0. There is the right of 0. Our very last function here, if I converted this to radical form, x plus 1 to the 1/2 is the same thing as square root of x plus 1. Because we are dealing with a square root function, we want to take out our radicand and set it greater than or equal to 0 and solve for x. So in this case, our domain is from -1 to infinity. We can verify this on our calculator. If we graph square root of x plus 1, we can see that the leftmost x value used is -1 and the rightmost x value used is infinity. I know this is a longer video. I've got one more question for you. Can you look at this graph and tell me what the range is? What is my lowest y value? The lowest y value is sitting right there on the x-axis. It's 0, and the highest y value is infinity. So when you need the range, look at your calculator and read it directly from the y-axis. All right, thanks for listening. I know this was a longer video, so good job hanging in there.